Every person who lives on this planet has seen a falling star, also known as a shooting star. I confess I sincerely believed such was the case, that these were in fact stars, much like I believed in Santa Claus. But then I heard the shocking truth. These are not, in fact, stars. When peering into the sparkling emptiness of the night sky, I watched as another meteoric body for the umpteenth billionth time tried to ram through the Earth's atmosphere. This happens constantly, day in and day out. Millions of cosmic bodies hurl themselves towards the surface of our planet every day. Really, there is nothing very special going on here. So, despite the apparent absurdity of the phrase, "Look, look, a falling star," it turns out that real falling stars do exist in our universe. Fasten your seatbelts, ladies and gentlemen. Once again, we set off into deep space. Meet Mira, or, as it is also called, Omicron Ceti. A sizable star, it is 700 times larger than the diameter of our Sun. It is an even stranger and more surprising star than Betelgeuse, the heroine from our last installment. The first mention of this beauty is found in Hipparchus in 134 BC, as well as in the testimonies of Chinese astronomers later in the year 1070. But its almost supernatural properties were discovered only recently. Pastor astronomer David Fabricius, quite by chance and without realizing it, discovered a new type of star on the morning of August 13, 1596. At that time, he was just watching Mercury, or rather, he was going to measure the angular distance from the planet to the star glittering nearby at an apparent magnitude of 3 in the constellation of Cetus. Interestingly, he had never come across it before, and it was also notably absent from all the stellar maps and globes. Though of course, maps and globes were not as accurate in ye olden days, and the disregard for some not very bright star was commonplace. Fabricius began to keep an eye on the stranger, and lo and behold, its brilliance grew right up to a magnitude of 2, and it became the brightest star in its constellation by the end of that August. But then in September, the star faded, and by mid-October, it had disappeared completely. In full confidence that this was a different new star, Fabricius stopped observing. But to his great surprise, he came across this mysterious traveler 13 years later on February 15, 1609. But to be fair, astronomer Johann Bayer managed to notice it about 6 years before this, in 1603. He entered the data into his famous star atlas, but had not yet suspected the super properties of his find. By the way, by that time, the star had already reached a stellar magnitude of 4. Various astronomers from around the world began to closely monitor Omicron Ceti for the next several decades. So, for example, the Polish astronomer Jan Hevelius, who observed the stellar body from 1659 to 1682, called it Mira, which is from Latin and translates as amazing. And he was absolutely right. This star is amazing. Usually, it is so dim that it is quite difficult to see with even a small amateur telescope. But due to its peculiarity, it becomes the brightest star in the constellation Cetus at certain times, the so-called peaks. Then it fades again and becomes almost invisible. And then again and again and again, everything repeats. Scientists finally, by the middle of the 17th century, established that this miracle represented a new type of variable star with a very long period of brightness and a very large amplitude. To put it simply, Mira is a star that constantly changes its brightness, but it happens with a fair bit of irregularity. The glitter of a star, for those who do not know, is its apparent stellar magnitude, the same as luminosity, or even simpler, brightness. Using the astronomical scale, smaller numbers are brighter. The brightness of Mira increases 3.5 times in just 332 days, from a brightness of magnitude 10, when it is almost invisible in a telescope, up to a magnitude of 2, when it becomes the brightest in its constellation. As I said, there is no pattern to her behavior. As a matter of fact, the period and range of brightness changes and is completely unstable. One time, Omicron Ceti went from the relatively dark 9th magnitude and then increased to the 5th and then back again. Another time, she faded to the 10th magnitude, but then shot up to her maximum brightest magnitude of 2. As you can see, the fluctuations in luminosity are simply immense. But what does all this mean? The luminosity of Omicron Ceti, aka Mira, at the minimum of its brightness almost corresponds or is even slightly less than the luminosity of our Sun. That means then that at the maximum, the brightness of Mira will surpass that of our Sun by 700 times, and sometimes by as much as 1,500 times the brightness of our Sun. The whole point of this is this. When red giants pulsate, the temperature of their surface also changes, which immediately affects the optical properties of the stellar atmosphere. As the temperature rises, the chemical compounds decompose and the atmosphere becomes more transparent. Also, a considerable role is taken by hot hydrogen masses, which erupt into the atmosphere during the periods of maximum brightness and further increase the brightness of the star. At least this is the most plausible explanation which I've managed to unearth of the amazing changes that regularly occur with Mira Ceti. And still, there is something more. Scientists noticed in 1919 that a second spectrum was superimposed over the Mira spectrum, and it belongs to a very, very hot white star. A satellite was discovered very close to Mira 4 years later. This hot little star is a white dwarf called Mira B, which, by the way, literally feeds on its much larger neighbor. Little Mira B orbits the giant Mira A only once every 400 years. And therefore, the satellite has made just one complete revolution around Mira A since the time of Fabricius. The average distance from the main star to the orbit of the white dwarf is about 70 astronomical units. That is to say, 70 times the average distance from the Earth to the Sun. And the most interesting thing is that this little dwarf star has similar properties to her much more voluptuous friend. The white dwarf also changes its brightness regularly. But this happens for several other reasons. Mira B has an accretion disk through which the white dwarf interacts with the main star, sucking away stellar matter from her much larger sister. Because of the unevenness of the supply of this substance, the luminosity of the satellite also changes. On average, the brightness value of the dwarf ranges from magnitude 12 to 9.5. It should be noted that the measurement of changes in brightness in stars of this type is a monumental amount of astronomical work. Just imagine, in order to obtain the amplitude of oscillations of the luminosity of a star for a period of 13 years, scientists need to take into account and superimpose all the fluctuations in the brightness of the star during this period. And their duration, by the way, is measured in minutes. And finally, we come to our last couple of delicious tidbits. The Galaxy Evolution Explorer satellite, also known as the GALEX, is an orbiting ultraviolet space telescope launched in 2003. The GALEX discovered a tail of matter stripped from the outer sphere of Mira A, like that from a comet, a gigantic tail of material the length of which is about 13 light years. So that you understand how long this really is, the distance from our Sun to the closest star is about 4 light years. That's a mighty long tail. Most of the stars in our galaxy slowly rotate around its center, moving about the same speed and in the same direction as the interstellar gas. In contrast to this, Mira is shooting through the galactic gas clouds at a speed of 130 kilometers a second. As a result, the matter thrown out by Mira is simply blown back, forming a bow wave tail of compressed gas. As calculations show, every 10 years, the star drops a mass equivalent to that of the entire Earth. To form such a tail, the star has taken at least 30,000 years. Oh, how I would like to see something like this up close. It is a pity that I would need to be a god to make it happen. A gigantic swelling located in front of the star is clearly visible in these pictures from the Galex telescope. This is the region of the shock wave. Something like this is formed in front of a boat's nose when cutting through water at high speed, or, for example, in front of a bullet moving at supersonic speed. This is matter thrown out by the star, experiencing a head-on collision with particles of interstellar gas. And here my story comes to an end for today. In conclusion, I should like to add that currently we have discovered more than 46,000 such variable stars in the Milky Way, and about 10,000 in other galaxies. And this is only the beginning, as more are being discovered every year. Put likes or dislikes if you don't like it, subscribe to the channel, share with friends and well-behaved acquaintances. Until next time.